think that it's time to make a start. So thanks everyone for joining this first meeting of the Prediction Modeling and Machine Learning seminar series, first meeting of the season, of course, because we have been for more than 10 years organizing this from King's College London. So for those of you that is your first time joining us, I am Raquel Iniesta, reader in statistical learning here at King's College London, and organizing this jointly with Professor Daniel Stoll, who's the head of the prediction modeling group here at King's. So we are very happy to be restarting these meetings this year, and especially happy because we finally have with us Paris. We were really looking forward to have you with us, and today it's going to be that big day. And Dr. Paris Lalousis is joined King's a few time ago. We were so happy to have him with us as a lecturer in artificial intelligence in mental health here at the Institute of Psychiatry, Psychology and Neurosciences. Very interesting stuff. He's currently leading the AIM lab, where he's using state-of-the-art artificial intelligence methods to incorporate multimodal data from phenotypic data, neuroanatomical, proteomic, and genomic levels. So by combining all of this data, Paris is aiming to improve the understanding of disease processes in mental health and mental illness. Today, he's going to be offering a very exciting talk entitled AI-based neuroimaging prediction of outcomes in depression and psychosis for both, and we are really looking forward to it. So when you are ready, Paris, I leave it to you. Thank you so much.
Thank you very much, Raquel, for a wonderful introduction, and thank you very much, everyone, for attending my talk. So, as Raquel mentioned, I'll be talking about AI-based neuroimaging prediction of outcomes in depression and psychosis. I'll start with just a little bit of background for the need for this prediction of outcomes in depression psychosis, and also why I'm using neuroimaging and why I think using neuroimaging within an AI machine learning framework is appropriate for this psychiatric question that we have. So as I mentioned, I'll do a little bit about the background for the interplay between psychosis and depression. Goes over 100 years ago. And I promise I will not go on too long on this slide. And I know some of you who are already attending here might have heard this before, but I think it would be beneficial for the people who haven't. So psychosis as a concept first appeared in 1841 as a shorthand for psychic neurosis. And even from then, in the 1840s, that emphasized the psychological manifestations of a disease of the brain by having that neurosis term in the shorthand. And then in 1845, Feuchtersleben has been credited with using the term psychosis for the first time as an alternative to mania and insanity, and again emphasizing that interplay between mental and physical processes. And it was not until 1891 that the concept of psychosis was narrowed down by Koch for meaning any disorder of the mind, as opposed to disorder of the nervous system, to meaning psychopathic inferiorities, and a term that was later renamed abnormal personalities by Snyder. And then in the last decade of the 19th century, brought Kraplin's very intricate work with 6 editions of a textbook on psychosis, where he made it culminated in 1899 with his separation of psychosis into manic depressive illnesses and dementia precox, with the latter being renamed into schizophrenia by Bloyer in 1908. And this split, this dichotomization has influenced psychiatry ever since and still influences psychiatry today. On the other hand, but we can see that there has been that emphasis on brain processes in psychosis ever since the 1800s. And then the concept of depression can be traced back to ancient Greece, actually, where descriptions of depressive state appear in the work by Hippocrates, where he called depression as a dysfunction of the brain. His explanation was due to excess black bile, which translates to melancholy in Greek, that's where we have the term melancholia. And it was not until the early 19th century that melancholia became a term that was dissatisfactory, and Geisinger attempted to unify all those terms and other forms of insanity under the term psychosis in his unitary psychosis hypothesis, which is the first ever concept of transdiagnostic processes, where Geisinger talked about the fact that more than one disorder might have a similar biological underpinnings. And then there's been a lot of changes in the description of depression, with endogenous, exogenous, reactive descriptions of depression. And in the DSM-3 in the 1980s, the term major depressive disorder appeared, and ever since it's been widely, although not universally, accepted. And there's still a lot of debate around these two terms. So enough about the history, but I hope you can see that it is a very intricate, two very intricate conditions that have really captured the mind of clinicians and psychiatrists and scientists for a long time. And we can see that there's always been that importance of how the brain is involved in those disorders. So in my work today, I'm going to talk about, sorry, I think somebody has their mic on. Yeah, thank you. So today I'm going to talk about neuroimaging and how we can use neuroimaging to predict outcomes in depression and psychosis. And the question might be, why neuroimaging? Of course, we can see that there's been a lot of research, neuroscientific research in depression and psychosis, but there's also been very little progress. So we've gained a lot of understanding about the mechanisms, mechanistic understanding of how certain processes in the brain might work, but this has not been translated into the clinic. Nobody uses neuroimaging to try and predict outcomes or treatment response, or prescribe a specific amount of a specific dosage for an SSRI or an antipsychotic. So, and why I'm going to show here is that the reason for this little progress is because inferential statistics don't allow us to do that translation, specifically for disorders that might have very little prevalence in the general population. So I've taken this slide from a really cool Nature paper, which talks about the fact that there's been little progress for neuroimaging in psychiatry, and they've got this example here. This is toy data, but for example, if you plot this, if you think the blue line are the healthy controls and the red line are the patients, and this is a brain measure of some sort, and here is the prevalence. So if you've got a prevalence of 25%, and you have an effect size of 2 for the difference, the group difference between those two groups in terms of some kind of brain measure, then that translates to a positive predictive value of 0.64 and a negative predictive value of 0.93. And of course, that is if the disorder at hand that you're looking at has a prevalence of 25% and an effect size of 2. And just as an example, these are the kind of effect sizes that we see usually in literature, with an effect size of 2 being deemed as huge, and you don't see that very often. I've given here an example for findings that we have for clinical high risk research, where effect sizes in using structural MRI data, functional MRI data, and MR spectroscopy range from 0.7 to 1.4. And of course, the prevalence is not that high, which means that in order to translate these findings into positive predictive values, negative predictive values that will allow us to make that translation, we need to have very high effect sizes to achieve that, especially in diseases where the prevalence is relatively low. I mean, for example, in psychosis, the prevalence is between 1 to 3% in schizophrenia, which means that the lower the effects, the lower the prevalence, then the higher the effect size you must have in order to have a meaningful translationable tool. And you can see here they've plotted it very nicely. If you've got a prevalence, for example, of 1%, the effect sizes you have to reach in inferential statistics are quite large if you want to have a tool of prediction. And of course, that comes down to the heterogeneity as well. In a lot of the times, even though there are group differences, there might be a lot of overlap between disorders and between healthy controls and patients. And my belief is that if we use AI-based methodologies such as clustering to disentangle that heterogeneity, we can then improve that that signature that we can capture from the data, that can then lead to tools that can be translated into the clinic and be personalized. So the first study that I'm going to talk about is a study that I did back in 2021, was published in Schizophrenia Bulletin, where exactly I was investigating what the heterogeneity is within recent onset psychosis and depression. So as we mentioned, there's a lot of heterogeneity between depression and psychosis, two concepts that are quite difficult to define. And of course, another thing that presents a problem is that the current diagnostic structures that we have are built on experiential terms and symptom groupings rather than a neurobiological basis. And that is also deemed to be a reason for the lack of biomedical translation in psychiatry, which also then leads to detrimental effects to disease and treatment course prediction. It means that because these diagnostic categories are not related to underlying biology, you might have a diagnosis, a similar diagnosis. So two people might have a diagnosis of depression, but their underlying biology might be very different, and also vice versa. Two people might have separate diagnoses. So one person might have a diagnosis of psychosis and another one might have a diagnosis of depression, but have very similar neurobiological underpinnings in their disease. And this is especially difficult to distinguish in early stages, which is why the work I'm going to present today is in early onset psychosis. And in terms of depression and psychosis, there's a lot of overlap. There's comorbidity and there's overlapping neurobiology in depression and psychosis. A lot of literature showing hippocampal and cerebellar gray matter volume deficits in similar areas across both disorders. And both disorders have been found to be pro-inflammatory states with similar cytokines such as IL-6, IL-8, IL-1RA, TNF-alpha, as well as others being found to be elevated in both disorders. So the research question in this first study that I'm presenting, it was, where do comorbid recent onset psychosis and recent onset depression lie within the affective psychotic continuum? And in order to answer that research question, the aim was to identify prototypes of pure depression and pure psychosis. So people who didn't have who had depression and didn't have any comorbid symptoms, and people who had psychosis and no comorbid symptoms. and then investigate the heterogeneity of depression and psychosis with common comorbid transdiagnostic symptoms. And to achieve that, we used 300 participants with recent onset psychosis and recent onset depression. We defined 2 pure groups, again, people who didn't have comorbid symptoms. And then we also had 2 comorbid groups. So these were patients who had recent onset psychosis, but also significant depressive symptoms, and people who had recent onset depression, but also significant psychotic symptoms. And we developed classification models using support vector machine in a repeated nested pool cross-validation framework. And in order to do that, we built a clinical and neurocognitive model using transdiagnostic measures of psychopathology. And we did that in the pure groups and then applied it to the comorbid groups. And then we also repeated that using a neuroanatomical model on whole brain structural MRI data and applied it to the comorbid groups. And then we also did the combined model. We used the stacking-based data fusion framework, which is basically a meta model. It extracts the decision scores from the classification models and combined.
Yeah, it's good, isn't it?
Sorry? Oh.
No, I just think that someone opened the microphone by mistake. Don't worry.
Okay.
Move on.
Yeah. We then, we use the stacking-based data fusion framework where we extracted the decision scores from each classification model and trained a meta model to basically assess whether the combination of those 2 different models increases the prediction in our machine learning models. We assessed the stability of our models with lots of different measures, so balanced accuracy, PPV, NPV, sensitivity, specificity, and area under the curve. As I mentioned, it was a repeated nested pool cross-validation framework with 10 outer folds and permutations and 10 inner folds and permutations to account for the difference in the class sizes. We had the C-value increased in the minority class by multiplying it by the inverse ratio of the training class sizes. We did a scaling, pruning, and imputation preprocessing pipeline within the cross-validation framework for all the different modalities. And we applied the linear kernel with 11 learning parameters. So we did some hyperparameter optimization, again, within the nested cross-validation framework. And we also had some feature selection, and then also did a permutation analysis to assess the statistical significance of our models. And this is what we found. So if you look into this this frame, we have the separation of the pure psychosis from the pure depression patients. And this is the pure clinical and neurocognitive model. Separates quite well. These are the pure people. They don't have any comorbid symptoms. So you would expect quite a high balanced accuracy. In here, we have a 79% balanced accuracy, area under the curve of 0.86. Now, if you look in this frame, so these people here are the pure psychosis people. These people here are the people who have psychosis, but also depression symptoms. Now, if you think this separation, anything above here is psychosis, anything below here is depression. Now, the comorbid people who have psychosis, but also depression, their mean classification is within the depression. So in the presence of comorbidity, psychosis people with depression look more pure depression rather than pure psychosis. So that was the first interesting finding in this analysis. And this this finding was across clinical, neurocognitive, and also neuroimaging models. And then in terms of the areas that contributed to these classifications, we saw that in order to be classified into the psychosis group, we saw that gray matter volume reductions in the thalamus and the cerebellum were really significant as features. And in order to be classified into the depression, the depression class, gray matter volume reductions in orbitofrontal, limbic, and paralimbic regions were quite important. Combining the two models with stacking did not increase the accuracy, which in my opinion was perhaps a good indication for that heterogeneity that I was talking about. So we see that the people with psychosis, when they have depression, they look more like depression, but that does not seem to be the same in the depression prototype. So here is the pure depression people. They're well within the depression prototype, and the depression people who also had psychotic symptoms were within the same feature space. So for this study, the conclusions that I made were that while there might be a small subset of prototypically pure individuals with clear categorical disorder, the majority of patients share a number of transdiagnostic features, primarily from the depression domain. And our findings suggest that clinical and neurocognitive transdiagnostic symptoms may have differential weight within psychosis and depression presentation with and without comorbidity. Now, in the pure groups, these symptoms could be seen perhaps under the hierarchical umbrella of psychosis or depression that may accurately reflect underlying pathology. However, in the face of comorbidity, which is the norm in a clinical setting, people rarely present with very clear-cut symptomatological presentations. These transdiagnostic symptoms lean more towards the depression domain. And the other thing was that there was this lack of biological validity. So the brain structures of the people who were classified as as depression, but had psychosis as the primary diagnosis, were similar to the brain structure of those people who had depression. So that shows a little bit the lack of biological validity of the current diagnostic frameworks that we have. And this led to the second study that I'm going to present today, which was published in Biological Psychiatry. And these are neurobiologically based certification of recent onset depression and psychosis, identification of two distinct transdiagnostic phenotypes. So the research question that I had for this study was whether we can identify clusters based on neuroanatomical data from patients with recent onset depression and psychosis, and are these clusters transdiagnostic, and do they perform better in predicting remission than the current diagnosis that we have, like the DSM diagnosis, with the aim to identify replicable neuroanatomical clusters across patients with depression and psychosis. So it was basically a bottom-up approach. So we just gave the algorithm the neuroimaging data without letting the algorithm know who has depression and who has psychosis, and let them identify clusters of similarity. To achieve that, we had 577 participants with recent onset psychosis and depression. You can see here unhealthy controls. You can see here the makeout of these people. We used whole brain measures derived from CAT-12 from 280 regions of the Neuromorphometrics Atlas parcellation. And then we also had a replication sample. So we took the model and then we applied that to the replication sample, who had roughly similar numbers of patients with psychosis and depression, but completely different sample, was not involved in the training of the algorithm. It was completely unseen data. Now, the thing with unsupervised approaches that had been applied in the field so far, such as k-means and other clustering algorithms, they usually directly cluster the patient population based on global similarities or dissimilarities, which sometimes might neglect the underlying subtle heterogeneity that's driven by the disease of interest. And there's been research that was shown, for example, I don't know if people here know about the Drysdale papers in depression, where they successfully developed some models some clusters that could then predict treatment response in depression based on resting state fMRI. But then those were not replicable because they reflected underlying nuisance variants of age, gender, body type, and genetics rather than specific disease-related variability. So to overcome those issues, I used a model that's called HYDRA, which stands for Heterogeneity Through Discriminant Analysis. And what HYDRA is a semi-supervised machine learning model because it uses the healthy controls as a reference sample. And by using the healthy controls as a reference sample, it ensures that every cluster that you identify in your patient population is not only different with each other, but each of them is different to the healthy controls. So the signature that you're capturing is disease-related rather than any other global signature that you might capture. So essentially what HYDRA does, it combines multiple max margin linear vectors and combines them in an iterative fashion. So you can have 2 clusters, 3, 4, 5, 6, 7, 8. The default is 2 to 8. And then through a measure of cluster stability that's called adjusted RAND index, you can identify which clustering solution is the most stable. So here's a visual of the model, with the blue dots here being the healthy controls and the red ones being the patients. So you can see that here we have 2 clusters that are separable from each other, but also separable from the healthy controls. Here there's 3, and it goes up in the number of clusters. In terms of the analysis details, first of all, because it was a multi-site study, in order to mitigate side effect on the signature of the imaging, we applied the combat harmonization technique. So combat utilizes empirical Bayesian framework that removes the variance which is attributed to scanner differences while also retaining the disease effects. And to further ensure that disease variance would be retained, that scanner variance would be disentangled from disease variance, the combat model was trained on the healthy controls, and then we applied the estimates from that to the patients. And we performed the repeated holdout cross-validation strategy with 1,000 repetitions, with 80% of the data for training in each repetition. We requested 2 to 8 clustering solutions. We did the combat site harmonization. The other good thing with this model is that you can add covariates. So we added age, sex, and total intracranial volume as covariates of no interest in the model. We used adjusted RAND index to measure cluster stability. ARI takes values from -1 to 1, with 0 being considered a random clustering and 1 a perfect separability and stable clustering solution. We then did a clinical analysis of the clusters, a voxel-based morphometry analysis of the clusters. We assessed the statistical significance of the clusters using permutation testing in 3 different ways. So first, we assessed whether the obtained subgroups were different to those which would be found in different disease structures by comparing the observed RAND index to a null distribution of ARI, which we created by randomly shuffling the features in the healthy control group and the patient group, and then permuting that 1,000 times in HYDRA, and then comparing that to the observed the observed model. We also assessed whether the obtained subgroups were different to those which would be found if disease-related variability was not present, by comparing the observed ARI to a null distribution of ARI that was created by randomly assigning healthy control samples to a healthy control group and also a pseudo patient group. So the algorithm would think that there was a patient group, but in reality they were healthy controls. So you create a null distribution that way by permuting it 1,000 times and comparing your solution. And we also assessed whether the data could be explained with clusters, or it could be better explained by a single Gaussian distribution by employing an R package called SIGClust, which tests the null hypothesis that the data come from a single Gaussian distribution by using a test statistic called cluster index. We then also did predictive analysis. So we had longitudinal data. So we created prediction models that predicted symptomatological remission at the 9-month point. And then we also did external validation to the replication sample and also 3 other samples from different areas of the world. 2 were schizophrenia samples and 1 was a depression sample. So I usually joke when I present this analysis slide and say that we tortured the data to make sure that our findings are valid. So the results showed that there were 2 clusters with quite high ARI of 0.618. One cluster had 153 patients, another one had 149. They were completely transdiagnostic, so it was not that one cluster had a majority of depression patients or psychosis patients. There was no significant difference of age or sex in those clusters, and they also survived all the different statistical significant tests that we did. In terms of the clinical presentation, we termed the clusters preserved phenotype and impaired phenotype. The reason for that was because one cluster showed a lot of PANSS positive, negative, and general psychopathology. So this is a measure of positive and negative symptoms in schizophrenia, showed a lot of negative symptoms, and also showed worse global functioning in a univariate comparison. But we also did a multivariate comparison to assess at the item level if there were any differences. And again, we saw that the impaired phenotype had a lot of these negative symptoms and also, I would say, biological depression findings, such as changes in appetite and sleeping patterns, as well as elevated cytokines such as TNF-alpha and CRP, which is interesting because these are people who had both psychosis. It was a mix of people with psychosis and depression. So you wouldn't necessarily expect that if you saw these people in the clinic. The preserved phenotype showed a more classic depression signature and also a couple of negative symptoms. And more importantly, we saw widespread gray matter volume reduction in the impaired phenotype. This is a comparison between the 2 clusters. I don't know how well you can see, but this is a univariate comparison between the 2 clusters that we identified. And you know how I was talking previously about effect sizes in these studies that are usually, you know, if you have an effect size of 2, then that's deemed a huge effect size. Here, the effect size goes all the way up to 9. And this picture here is you'd usually associate this with a schizophrenia comparison. These are people very recent onset, and they're not just psychosis, they also have depression, which was again a very interesting finding. And then we see the feature weights for the inflammatory markers that I mentioned before. The clusters externally validated well in the replication sample with a balanced accuracy of 94% and an ARI of 0.5. 0.57. And then clinically, the really interesting thing was, as I said, we did some prediction modeling of 9-month symptomatological remission. And what I wanted to see is if I take the same models and I do this prediction modeling in the traditional diagnosis, so recent onset psychosis and recent onset depression, and then I also do it with these more neurobiologically based subgroups, is there an additional effect for predictive utility? So I basically used very clinical variables and some inflammation, and I did the stacking based fusion that I mentioned before to predict 9-month outcomes. And I did the same pipeline in all those different cohorts. And what we saw is that the preserved and impaired phenotype together have a very much higher and statistically significant higher balanced accuracy in predicting 9-month outcomes, which shows that neurobiologically based transdiagnostic clusters can more accurately predict symptomatological outcome compared to the traditional DSM diagnoses that we currently have. We also, like I said, externally validated in 3 other data sets, 2 schizophrenia ones, 1 depression. These people had a higher range of duration of illness and AIDS. And what we saw is that somebody who has longer duration of illness, more chronicity, higher AIDS, across depression and schizophrenia, they're more likely to be put into the impaired cluster. And the cool thing about that is that these people, you can see here their age is between, the mean age is between 34 to 42. But the models that we developed are in recent onset psychosis, which have a mean age of 23, which points to the perhaps finding that we could have these recent onset models that can predict poor outcome and chronicity at an early stage, which is very clinically relevant. So to conclude this study, we have 2 transdiagnostic clusters based on neurobiological data and semi-supervised machine learning approach, and they're generalizable to the replication sample as well as 3 other external validation samples. The impaired phenotype was characterized by more symptom loading, functional impairment, gray matter volume loss, and elevated CRP and TNF-alpha levels. The preserved phenotype had more central depressive symptoms and less impairments, and we had this widespread gray matter volume reduction. But in terms of the clinical importance of the findings, the neurobiologically informed clusters outperformed traditional diagnosis in predicting symptomatological outcome and also predict poor outcome and chronicity. And I've got a couple more slides where we have this, one of my PhD students in the Max Planck Research School for Translational Psychiatry in Munich is doing basically a similar approach, but instead of using structural MRI, she's using resting state fMRI. Her name is Madalina Buchiman, and she's very kindly shared slides with me so I can show her work. And she's finding similar results where there is a preserved and an impaired phenotype characterized by worse connectivity, and that translates in characterization with clinical, cognitive, genetic, and functional outcome characteristics. And she did that with 30 subject-specific mode amplitudes from brain imaging. And basically, what is showing here is that the preserved biotype had higher activation in most of these components. Yep. But the impaired biotype had increased activation in occipital and limbic regions, such as the thalamus and the orbitofrontal cortex. And these subgroups also can be classified compared to healthy controls in above chance level. The impaired biotype is more separable from healthy controls based on a similar pattern of overall lower component amplitudes. And the preserved biotype even shows increased amplitudes relative to the healthy control sample, which can point towards some overcompensation of the resting state, the resting state networks. This is all the different components that Madalena identified. And also, interestingly, very recently, we saw that these clusters show persistence of symptoms, and they can predict that persistence of symptoms better than we can do in the traditional diagnostic categories. So yeah, these are really hot off the press, like really analysis that were done within the last week or so. We are really interesting, and I thought it'd be useful to show here. So that concludes my talk. Thank you very much for listening. Thank you very much to my lab, who are all named here. Nice picture of us having dinner in London, and also collaborators and friends. And if you have any questions, feel free to ask me now, or you can send me an email or reach out to me on social media.
Excellent. Thank you so much, Paris, for such excellent presentation and excellent job in the work that you were showing. Fantastic. So I'm sure that the audience will have lots of questions and comments. There are people that are already clapping hands.
Thank you.
Really well done. And is there any question, any comment from Paris? So please just raise your hand and you can open the microphone, or if you prefer to type it in the chat, I'm very happy to read the question as well. Well, I have a first question, if not. It's about the clustering method that you use. So just a very quick question. Did you check any other, let's say, more state-of-the-art or known method for clustering the data, and to compare if you were already getting these two clusters? That's the first question. And the second question is that if your intuition, original intuition, it was that you will find two clusters, or you were expecting to find more than two?
Okay, yeah. To answer the first question, yes, I've not presented that here, but we did a couple of different clustering techniques. We also used, for example, K-means. We also used some deep learning algorithms with some adversarial networks to find clusters. And again, what we were finding is that those clusters were showing signature that was not related to disease, but rather than more global findings. So that semi-supervised approach that uses the healthy controls as a reference sample really ensures that the signature is related to disease rather than variants that might be interesting to find but not so clinically relevant.
Mm-hmm.
And then the second question, if I thought that there would be two, no, I didn't. I thought there would be more. Yes, I thought there would be more. Since I've published that, quite a few other people have used similar approaches, and it seems that in terms of brain data, whether that is structural MRI or resting state fMRI, two biotypes always seem to emerge. There can be a lot of speculation as to why that is. It's not methodological because I've used the same clustering algorithm with inflammatory data. And in that case, I find 5 different clusters with different immune pathways. So yeah, it could be that perhaps when it comes to brain, the cluster identifies perhaps a risk phenotype that shows that people are more receptive to medication and others are less so. That's we could talk about that. I've had this discussion with many people about why that could be.
That's very interesting.
Yeah.
We have other people. Thanks for the answer, Paris. So we do have other people asking now. I think that the first one was Sandra. Please, would you mind to make your question? Thank you. Sandra, you there? I think you were raising your hand, or you're not raising it anymore. Maybe your question was already answered. And I think you got other question from Sun Bin Kim is in the chat. The first one is, how could you define subtypes of fMRI activity?
Yeah. So with I assume the question was with task-based fMRI. Is the question for task-based fMRI? Because like I showed resting state fMRI where we can do that. In terms of task-based fMRI, I'm always a bit more skeptical for using task-based fMRI for these kind of analyses because of there's a lot of paradigm variation between different centers where they analyze fMRI. I suppose what you could do is take, you could extract the values from the task-based fMRI that you might have, and then use those as your variables, your features for like the similar approach that I used. But I would say if it's task-based fMRI, then similar to what I presented, it would need a lot of external validation, because I feel the variability in task-based fMRI is also much higher than it is in structural MRI and resting state fMRI. And then there's a question of whether it's made with static points or a series of activities. I'm not sure
you understand. Yeah, maybe soon you can clarify. I cannot understand the question either. Sorry. Maybe you missed some words. If not, in the meantime, maybe Jim, who's also raising his hand, can ask. Jim?
Yeah, so thank you so much, Paris, for a wonderful talk. So I have two questions. The first one is regarding the dimensionality of a structural MRI. So especially for your first project, it seems like you fit around like 800 features, or lots of features, and you only choose a gray matter variant. So I'm thinking about, will you do any feature selection before you put it into your model, on why you only choose gray matter variant instead of other cortical thickness or other modalities quite common you can retrieve from structural MRI? That's my first question. My second question is regarding the subtype that you cluster from there's two bio subtype. One is preserved one, the other is more impaired one. I just wondering, is there any difference in terms of the duration of illness? I'm thinking about because I want to know whether they are naturally different, or they are just in their disease trajectory. Yeah, thank you so much.
Yeah, thank you very much. These are both excellent questions. So in terms of the first analysis that I presented, yes, we did some, maybe I didn't put it in the slide, but we did some PCA to do some dimensionality reduction for the neuroimaging data, because it was not parcellations, but it was voxel based. So there was like thousands of features. And then within the cross-validation framework, we had a greedy forward feature selection wrapper to select the most significant variables, so we can further reduce the dimensionality of the data. And then in terms of your second question, which is I think really really good question. There was no difference in the duration of illness in the phenotypes. These are recent onset psychosis patients who were and depression patients, all of them within the first 3 months of presentation of symptoms and minimally medicated. So there was no difference in the duration of illness between those two subgroups, which makes the fact that we could then predict chronicity and poor outcome even more interesting.
Thank you.
Yep.
Thank you, Paris. There are two questions. I can read them. The first one, these are by Ria Alama. So first question, in your research on psychosis, what specific genomic variants, or proteomic markers have you identified as being most strongly associated with neuroimaging abnormalities? And how do these biomarkers differ between early and late stages of the disorder?
Mm-hmm. Yeah, and then there's a second one. How has AI assisted?
You can maybe answer the first one.
Yeah. I'm just reading both to see if there's a relationship between the two questions. Thank you. Yeah, both really interesting questions. So we're currently doing some analyses where we're looking at the genomic and proteomic markers that are associated with the findings that we've had within this cohort. Interestingly, what we find is that a lot of inflammation-related markers are predictive of the brain patterns that we are finding in these results. And we're actually doing an analysis currently where we are looking at the relationship of those markers with the brain patterns that we're identifying. And it's also related to when I said that I've applied the same clustering algorithm in some inflammation data where we see different pathways of inflammation that are specifically related to very specific gray matter volume patterns of findings. And then how do these biomarkers differ between early and late stages of the disorder? So with the proteomic genomic markers, I've not done a lot of work in late stage disorder. It's all within the early psychosis and depression framework. And I think it would be a really interesting question to answer. I know that there's a lot of work that's currently being planned to be done. So thinking again, it's again around that inflammation story, where the same way how we have brain aging, accelerated brain aging, some people might have accelerated inflammation aging that is also not only related to the brain, but also multi-organ inflammation that can lead to these psychiatric symptoms. And there's somebody who has published some really nice results on multi-organ inflammation that I can send to you if you're interested. Sorry, that was a very long answer. The second question, how has AI-assisted neuroimaging reveal novel patterns in brain connectivity related to synaptic dysfunction depression? So in terms of brain connectivity specifically in depression, the work that I've done is transdiagnostic across psychosis and depression, but Cynthia Fu, who's at King's, has recently published a very interesting paper where she has found some recent some interesting findings using Hydra, where in depression, identifying two biotypes that can then predict treatment response in depression. Let me find the paper and I can put it in the chat. And also Leanne Williams from Stanford has recently published a very interesting paper on resting state fMRI biotypes in depression. And I think they would both be better at describing that because it's their work rather than my work. But I can put the papers in here. I think they're both really, really interesting and good. I don't know if there's any other questions. Daniel.
Yeah, I've got a very naive question. As a person who doesn't know a lot about fMRI, how does the scanner itself affect your imaging recording or the sort of brain response? So I guess people with psychosis will respond automatically different than if they come to a scanner, which might be a very frightening situation for them. I guess it's a question you asked many times, but I didn't work with fMRI so far.
Yeah. Yeah, I think it's a very good question. And it's also another reason why I'm a bit also very careful with task-based fMRI. So structural MRI will not be affected based on the experience that somebody's having in the scanner, but task-based fMRI will do, and it will affect the way that the signal is being produced while in the scanner. But also perhaps that reveals some interesting findings about how different. I think it's I think in the end it's a signal that is of interest, right? Because somebody who has psychosis will react differently in the scanner than somebody who has depression. So that signal in itself might be indicative of specific disorder-specific signatures in the brain. I don't know if that answers your question or.
Yeah, I think that answers yes. Okay, great, thanks. But just to say, it was a really great talk, and I think it's very good to hear. If you don't have a perfect prediction model, you can't implement a clinical practice. You showed that you can still learn a lot about it, and I think you provide a lot of new insight into the neurobiology of the mental health disease. I think it was very exciting, and I think I will come back to you at a later point with the Hydra clustering. That was really interesting. But
thank you.
Thanks.
I think you're muted, Raquel.
Sorry, I just muted it. No, I was just saying that I think I will go back to you as well about the Hydra clustering method, so you'll be very busy. So I think that there are no more questions, 2 minutes to get to the 4 o'clock. So so thanks very much, Paris. It has been absolutely great, the talk, the work, and the discussion. So really, really happy to having had you here with us today. And for the audience, just letting you know that the next meeting will be on 13th of October. We will have Dr. Lorena Escudero Sanchez talking to us she's from Cambridge, and he will be talking about her work on AI applications to radiological image analysis for cancer. It promises to be very interesting as well. In the meantime, please take care of yourselves, and we'll see you very soon. And thanks, Paris, again. Have a very lovely evening. See you all.